Now I'm very happy to welcome on stage the Kavli Prize Laureate, David Charbonneau. David is searching for life in outer space, and he is also searching for exoplanets, a planet that orbits a star outside our solar system. David was born in Canada and works now as a professor at Harvard University in the US. So David, what is your prediction? Is there a life out there? And what kind of life? Welcome on stage.
Okay, we're doing a lot of really fun things during this week. You're all going to stick around for what's about to happen in a couple hours, but I'm really looking forward to this. I really enjoy talking to students. I'm an astronomer, and I think I'd like to start with asking a question about why should we study science? Why should we pursue science? And often you hear that we should do it because of the benefits for treating disease, right? And that's really important. I'll share with you that actually I have cancer. I have very serious cancer. I care deeply about the developments for personal reasons and also for friends and family who are afflicted by all kinds of disease, right? We need it for the public defense, unfortunately, okay? We do need to look after the security. We need to monitor computers, and for physical attacks, we need to make our country safe, our community safe. That's a common reason for developing technology that goes back hundreds of years. You might say we want to make our lives more comfortable, right? We want to have smartphones. It makes our life more enjoyable. And I think the question I would like us all to think about is that enough? If you're healthy and you're safe and you're comfortable, has science done everything that it can do? Okay? And I think all of the laureates would, of course, tell you that the answer is no, right? There's something else much more profound that drives all of us, which is a real, genuine curiosity in fundamental questions about the physical universe. And actually just pursuing that in its own sake is one of the most profound things that humans can undertake, okay? Just in in that way, it's almost more akin to the profound sense that you get with art, okay? Or with great literature, when we explore the human condition, okay? And so, you know, astronomy is really, I mean, I don't think there's a lot of direct benefits to astronomy. There certainly are over time. There's all sorts of things that were developed with an interest initially towards the stars, now have a great application in our day-to-day lives. But when we undertake the study of astronomy, it really is by embracing this idea that we just want to go after those most fundamental questions. So the question that I really became passionate about was looking for planets around other stars. Could there be planets around other stars, and could there be life on those planets? When I was your age, we knew nothing about planets around other stars. We wondered about it, okay, but nobody had ever found a planet around other stars, and if you asked about it, everybody said they would be impossible to detect. They're so small and they're so faint, okay, compared to their central stars, that you shouldn't even try. These, I hope you recognize these, yeah? Okay, so these are the 4 rocky planets of the solar system drawn to scale, okay? So you've got Mercury, Venus, Earth, and Mars, okay? There's other planets, bigger planets, gas giant planets, but of course these are the ones that really fascinate many of us the most, because one of them is home. And if you were an alien astronomer looking at the solar system, okay, from afar you would recognize that there's something really different and special about that third planet, okay? It's covered in liquid water. The other planets don't have that, okay? The rock that you can see is covered in a green stuff, It's not brown. It's not the color that rock is. And if you were to study the gas, if you were to study the atmosphere of this planet, you would notice that there is a lot of this molecule called oxygen. And you would know, you would say, well, oxygen is incredibly reactive. How does that stay? I mean, it would react with the rocks. It would rust the iron. Why is there so much oxygen in the atmosphere? And of course, the answer is that there must be biological activity that's driving that oxygen, allowing for there to be 20% oxygen. Okay? So the idea is that gazing from afar, we can be the alien astronomers, looking at other planets orbiting other stars, and by studying the contents of the atmospheres of those planets, we could actually deduce that there must be biological activity, photosynthesis in this case, indicating the presence of life on the surfaces that those atmospheres envelop. Okay. But I also want to tell you a bit about my own, I was asked to tell you a bit about my own path. And so I wanted to share some photos, okay, of myself. All right, so this is life in Canada in the 1980s. Now, in the United States, there's this incredibly popular show we all love, Stranger Things. Does anybody watch Stranger Things? Have you ever heard of the show? Oh, it's about a band of kids in the 1980s. They ride around on their bicycles, they play Dungeons and Dragons, and they also, of course, are very involved in science. So this was my life growing up in Canada. Hockey, ice hockey was incredibly important. Everybody plays hockey in Canada. I would often go out into the woods and go camping and explore nature, okay? But I was a profound nerd, okay? I really, really loved science fiction. Okay, I'm going to share a photo with you. All right. On the right, okay, over here, you've got Luke Skywalker from Star Wars. Okay, he flies the X-Wing fighter pilot. Okay, he's going to go defeat Darth Vader. And here is me in second grade, dressed up in the same costume. But what's so touching about this costume is actually the orange suit that I'm wearing to mimic Luke Skywalker is actually a biohazard suit that my mom, who was a scientist, who worked in a lab studying toxins in the environment, borrowed permanently from the lab, dyed orange, and then together we fashioned it into a Star Wars Halloween costume. And in October, everybody dresses up in various costumes, and we all go around and get candy from our neighbors. Halloween, it's awesome. Okay. Books were incredibly important to me growing up, and these are the two most influential books, okay, that I read while I was in middle school and high school. I was a huge fan of fantasy and science fiction. I really was affected by books by Ursula K. Le Guin, one of the great science fiction writers. And in particular, she wrote this amazing story called The Wizard of Earthsea. Okay? Now we're inundated in fabulous books about fantasy and science fiction. At the time, there were very few, and this was one about a young person learning about the real nature, the true nature of the world, and of course, the true nature of himself. This book is probably the reason I studied physics in university, okay? I loved science growing up. I loved astronomy. But this book, written by Stephen Hawking, talked about ideas that I'd never heard of. It talked about quantum mechanics. It talked about general relativity. I would sit out in the hot summer in Ottawa in the driveway in front of our house, and I would read this book. And I realize now that it was the strangest poetry. I didn't really, of course, understand quantum mechanics in high school. How could I? There was no equation. There's one equation in this whole book, and he laughs about it. But there was something deeper that it was connecting to, and that really got me hooked. And with the encouragement of my parents, who were both scientists, my dad was a geologist who would go up north in Canada and explore the geology of Canada. My mom, as I mentioned, was a toxicologist. With their encouragement, I went off to study physics. Okay? Another really important part of my life was scouting. Okay, was going out and and learning not just about the outdoors, but learning about leadership. Okay, and so here is a group of scouts, and we would go canoeing throughout the woods in Canada, and often in very, very rainy and wet conditions. Okay? But the point is that we also learned a great deal about how to work as a team. Under honestly, the sorts of trips that if I look at now were, actually we're extremely demanding, like 2-week-long canoe trips with no support if anything went wrong. This is me graduating with my parents and my sister at the University of Toronto. You can recognize the very distinctive building in the background. I want to tell you a bit about the support of my family. My mom is a refugee. She's a refugee from Latvia, and she escaped during World War II. At the time, refugees, when she arrived in Canada, they were treated terribly. They weren't welcome at all. They were not allowed to really take up any interesting jobs. They weren't supported. But her father really made a point of really getting all of his kids to get a great education. She became a toxicologist. She worked for many years in the government. She was a great doctor. They're still alive. They're still doing well. And then a psychiatrist for many years when she lost her vision. Okay? So, you have to think about that path, right? And how important it was that she was allowed to pursue that path. And then to encourage me in science. My dad grew up very poor in Canada. His dad was a milkman. But was also able to go. So access, that access to education, right, really was transformative for me, right? I wouldn't be here if it wasn't for the opportunities that both my parents and that I think Canada provided for them, for all of us. Okay, I want to talk a bit about my scientific path, and the most important thing is I do want to get to some questions. I think this is my first research experience. This is my very first year of university. So I think you're going to go off to university like maybe next year if you're going to university. Are you at like last year of high school? Yeah, right. Okay, so here I am in a chemistry lab. When you arrive at university, I received a physics book. Okay, it was 800 pages. It was chock full of equations and facts and plots and diagrams. Right? And I really, really studied physics. And what nobody stopped to say was on day one, just so you know, 95% of the universe is stuff that we know absolutely nothing about other than its existence. Does that blow you away? So 5% of the universe is this stuff. Atoms, molecules, electrons, protons, what we call baryonic matter mostly. 25% is something called dark matter. We don't know what that is, but we know what it isn't, if that's helpful. And then we have 70% is something called dark energy. And we only know, the only thing we know about dark energy is that it makes up most of the universe and it propels things apart from each other. We have that's honestly it. There's not even really useful equations that describe it. Here I am in the first chemistry lab, and I was very, very thankful because the mentor in this chemistry lab basically gave me a very interesting open-ended problem and just set me loose, and I was allowed to use any chemicals I could get my hands on in the lab. I could order more chemicals. I could do any experiments. Every so often, the postdocs in the lab and the graduate students in the lab would go to the PI and they would say, are you sure you want him doing those things? And the PI said, just let him do things. It'll be interesting. And I really fell in love with experimental science. The other connection I want to make is that, I don't know what your experience is here. My experience in high school was the teaching of science was very much about the learning of the theory of physics, so the equations of physics, how to solve the equations, and the facts of physics and biology, okay? But there was no real exposure to the actual thing that I do, which is research, which is true open-ended inquiry. And that's okay. We do want to equip you with those facts and those methods. But you have to understand that the job of a scientist has really very little to do with the experience of being a student of physics in high school. Okay? We do want you to be a student so that you get the basic knowledge. But really what drives scientists is curiosity, is passion, and it's often a very hands-on job. Okay, many of us are working with our hands, we're building things in the lab. I spend most of my time, I go out to mountaintops, it's extremely beautiful, I build things with students, and we measure, okay? And I need all of that physics. You do want to study and do as well as you can in your classes, but if you feel like math or science didn't come naturally to you, don't talk yourself out of a job in science, because that's not the key trait that really matters. The key trait that matters is curiosity and I would say a drive, okay? Okay. And then the last thing I wanted to show was, this is my very first experiment that had a real success. There was a whole series of experiments that had no success before that. And this is a tiny telescope. The lens is about this big. And I went out to Colorado. After having a couple years with no success at all at Harvard, my advisor said, you should go out to Colorado and try something new. And I went out to Colorado. My mom came and visited. I wanted to show this to connect with my family. Here's the telescope right here. And what we measured was the first time that anybody ever saw a planet pass in front of its star. Okay, and then that's now the way that most planets have been found. 6,000 planets have been discovered by that method. New planets are found by that method every single day now. Every day we find new planets with missions that I'm part of that are up in space, which are enormous investments from the astrophysics community worldwide. But it all started with this very, very humble telescope out in Boulder, Colorado. Okay, and then I went on to build other experiments, including series of telescopes in Chile and all over the world. Okay, so I wanted to give you a bit of flavor for my my path in science and also a bit of what we do. But most importantly, I really would like to answer any questions that you might have on either of those.
Thank you so far, David. Bent and Beate is going to work the floor with the microphones to pick up your questions. But I have to ask you again, did you say every day
Yes.
you are finding new planets?
Yeah, no, it's an amazing, so, I grew up, I cared about Star Trek. In Star Trek, every star has a bunch of planets. Actually, that is the universe. We didn't know that when I was growing up, but that actually is the world we live in. We've discovered that all stars have planets. And now we're surveying them with a satellite called the TESS survey. And actually, you can look at the data. The data are public. I don't get the data before you. One of the things we did with the satellite was we made it pure public. And it is constantly finding new planets, yeah.
So who would like to start? We got a question here, yeah.
Can you only find planets if they orbit in front of the star?
Peter,
I can repeat it, and then we can figure it out. Yeah, so can you only find planets if they orbit in front of the star? No, there's other ways to find planets, okay? So the idea is if there's a planet orbiting another star, the star will gravitationally orbit the planet as well, and so it'll go towards you and away from you, and that change in speed is something we can measure. And then for, that works even if it's not exactly aligned, but if it is aligned, if we do see the planet go in front of the star, then you actually can measure the size of the planet, and because you can measure both the mass from that wobble and the size, you have a density, and then you know what the planet's made of, but you can also do the most interesting thing, I think, which is you can look for the light from the star passing through the planet's atmosphere and study the atmosphere of the planet. And so hundreds of these 6,000 planets have been found, several hundred have already had their atmospheres probed for molecules. So the transit geometry is very, very special geometry.
Thanks. We got another question, yeah?
I want to be an astrophysicist when I grow up, so do you have any advice or about anything, really?
Yes, I have lots of advice. So I would say that one very important piece of advice is to not be deterred if your first or second research experiences don't work out, okay? So my first research experience in astronomy at the University of Toronto went terribly, okay? My advisor didn't like me and thought I was lazy, okay? Basically told me he thought I was lazy. And I don't blame, like I really just realized, no, it was just a bad fit, okay? But the important thing is to continue pursuing it as long as you're putting in the work and the effort. And I think that many of us have stories of things that didn't work out the first few times. The other thing is how important it is to develop your skills, all of you, at communication. When I was learning to be a teacher, one of the most influential lectures I went to, there was a speaker who for many years taught science education at MIT. And what he said was the following. He said, as you make your way in science, you will be evaluated upon the quality with which you speak, the quality of your writing, and the quality of your ideas in that order. So you do have to have good ideas, but we are all familiar with friends and colleagues who have fabulous ideas, but they don't take the time to think about how to communicate them. And science without communication is no impact. So a little bit of advice.
Lovely. Another question. The microphone is over there. Yeah, please.
How did your first experience finding the planets differ from previous tries from other people?
How did my experience for finding the planets differ from
previous experiments trying to find planets?
Oh, yeah. Well, the big change was that at the time, most people thought that planetary systems around other stars would look like our planetary system. So they assumed that the universe was homogeneous in that way, okay? And so what that meant was the only planets that were big enough to block enough light that you could see them by this eclipse method, which were Jupiter and Saturn, were out where Jupiter would be, so they would take 12 years to go around. And so you would never see a transit, right? You look for one night, but the chance that you see a transit, and also the probability so far away, the probability that it's exactly aligned would be almost zero. What happened with us is that we went looking in a range of parameter space where most people thought there wouldn't be planets, but that we were sort of more open-minded maybe, and there were some other astronomers who were as well. And we found, of course, discovered this class of objects called hot Jupiters. Planets that are the size of Jupiter, but they go around every 3 days. They're much closer to their star than even Mercury is from the sun. And so other people could have found those planets before we did, but it was really that we were searching in a parameter space that other people had ruled out for there were very good physics reasons why you wouldn't have a big planet close to its star, which has to do with planet formation. Nature is always going to outcompete you in terms of creativity. Nature is much more creative than humans are. Okay, so be open-minded.
Have we got a question on this side?
So is your first successful science experiment one of the main reasons for finding new planets, or one of the main ways we use for finding new planets?
Yeah, so I was the first, the first transit, that was that image I showed you of my mom, with that little telescope. That was 25 years ago as of Monday, okay? So on Monday is the 25th anniversary of that. But then there were none for many more years, and then we found a whole bunch. But basically, as I said, now we find, that by that method, we find them every day. And really only with that method, those subset of planets that go in front of their stars, those are the ones where we can actually study the atmospheres as well. So that method, which is a very simple method, when you go to space and you can make precision at sort of a level of parts per million, then you can find Earth-sized planets. And that's what is really where the field is now, is looking for planets that are really just like the Earth, but discovered through this eclipse method. Yeah.
So we have one final question now.
How do the characteristics of newly discovered planets, such as atmosphere, distance from its star, and orbital path, contribute to like a possibility of supporting life or not? Well, I would say that so far what we're doing is we're finding rocky planets, and we want to find rocky planets
So we think you have to have a rocky planet because we think you need a surface, and then you need a liquid ocean. So the planet has to be the right temperature. Okay, so we are now able to find planets that are not just rocky, but they're in their habitable zone. And so I worked on a study using data from the NASA Kepler mission with a student at the time, Courtney Dressing. Courtney's now a professor at Berkeley. And what we deduced was a really amazing conclusion, that actually 1 in 4 stars in the galaxy has a planet that is not just the size of the Earth, but also is the temperature of the Earth, so it would have liquid water on it, okay? That's amazing, right? If Earth-like planets orbited only 1 in a billion stars, or 1 in a million, which is possible before we started, then the closest one to us would never be close enough that with any realistic telescopes we could hope to actually study it and look for life. Now we learned that even if we look at the closest 4 stars or 8 stars, there will be a few examples where they have a habitable planet. So it's a very, very real possibility that in the next 10 years, okay, we, using newly developed telescopes such as the James Webb Space Telescope, we actually would be able to study the atmospheres of these worlds and really conclude that there's this molecule and that molecule and that molecule, and that really, in aggregate, those can only be explained through biological activity. So it's a really exciting time. You know, there's only one first time in the history of humanity when we learn that we're not alone. We all might be alive for that moment. So.
Yes, thank you. That was a wonderful way of ending your talk, David. We really appreciate it. Thanks.
My pleasure.